Hello and welcome to 12th lecture in 5th chapter in comprehensive course on AI, ML and DS. In previous lectures, we talked about measure of central tendency, mean, median, mode, etc. And we also talked about measures of dispersion or measures of spread of data like variance and standard deviation. However, rather than finding say mean by np.mean, then median by np.median, in bracket of course the data which must be passed as a numpy array, or variance by np.var, and standard deviation by square root of variance. Instead of doing all those things, if we use Scipy library, which we know that we in any case have to use, because for example harmonic mean and geometric mean we could not find from NumPy library, there are no functions built in, so Scipy library we used. Similarly, skew and kurtosis we could not find functions from NumPy library, so we use Scipy library. So in any case we are using Scipy library in this chapter, and some NumPy and Scipy both are actually very closed. They are both NumPy numerical Python. It is library for numerical calculations using Python. Scipy is also a library for calculation only, but for scientific calculation, because in common daily life this skew, kurtosis and geometric mean and harmonic mean, they are not much required. So that is why Scipy is kept as a separate library for more sophisticated functions. But that Scipy has a very big one advantage. It has one function. That function is called describe. So you just write, first import of course library, and just write describe in bracket your data, and the data must be passed as a NumPy array, and you will be surprised that in just single line of code you will get mean, then variance, range, minimum value, maximum value, then variance, standard deviation, skew and kurtosis, everything in just one single line of code, describe in bracket data. But for that you have to first import Scipy library, and you import the describe function from that Scipy library. Okay, so let us see that. Here it is written from scipy.stats, stats stands for statistic, import describe, and then data equals np.array, and then we are taking a list of 1 to 16 numbers. So we know that a list when passed to np.array function gets converted into a NumPy array. If I check data type of this, only this much shaded portion, then that would be list. But if I check data type of this whole thing, or that means data type of this data, then I will get ND array. So that is NumPy array, 10-dimensional array. And that's it. Just once you get your data, then you just write describe in bracket data. That will give all the statistics in one line of code. So that will give number of observations 16, then minimum and maximum value, then mean, then variance, then skew, then kurtosis. So you can see the power of this, that there is no need to use np.mean, np.variance, then from Scipy import skew, then skew of data, kurtosis of data, separately 4 different functions. Everything is included in there, and it also includes the range, min, max, and number of observation. So a super useful function. Okay, so keep this in mind. Now this other one is also example of use of Scipy.stats library. Okay, so we have imported describe. Here I think import stats and from Scipy.stats import describe. That is what it should be. Okay, right. And then we use stats.describe data, just like here. Okay, here fine. Now I can just write describe data. That is okay. Now here my data was just a simple list like this. Compared to that, here data we are generating by a NumPy function. This also, the purpose of giving second example is this, that earlier we had seen one function that is called np.random.randint, random integer. Okay, so that gives me what? That randomly generates some integer in the range which you have specifying, that for example 2 to 12, then it will generate randomly the integers between 2 to 12. Okay, and each time you execute the function, it will give different random integers. Similarly, this is NumPy np.random, so again randomly generate, but at least this time it is not generating integers but rather some numbers which are automatically normally distributed. And here what you have to specify is these 3 parameters, that the minimum value of your data, maximum value of your data. So that means all those numbers which you are generating should fall between 0 and 1, and size of sample. So size is 1000, means create 1000 numbers between 0 and 1 which follow normal distribution. So that is something like this. Okay, this is 0, this is 1, so it will create several data points between 0 and 1, like this, total 1000 data points, and these data points would be normally distributed. I am drawing with mouse, so perfect bell curve is not seen, but actually if it is normal distribution, then it will be perfect bell curve. Okay, fine. Now then, descriptive statistics can be easily found by just describe data, and if you write it, then cannot import the name of describe, spelling mistake, sorry. Okay, so you can find number of observation, minimum and maximum, mean value, variance, skew, and kurtosis once again by just one single line of code, describe data. Okay, so that will give the description or statistics for my this normal distribution. I can even plot this if you want, then it will give exactly this kind of distribution, that is the Gaussian distribution or bell curve. Okay, what next is this? This is another concept which is important, that is finding correlation coefficient. And NumPy has one function called core-coff. So that is CORR, correlation, and COEF, that is coefficient. Okay, between what? Between any two data sets. So X and Y. So here I am taking one data set is np.random.rand and 100. Okay, and if you want to be still clear what it is generating, then I will add one sentence print X. So you will actually see that what is getting generated. And that second is again almost similar. Again I am generating random normal only, but this time I am adding some constant, not even constant term, but a linearly varying with x term to x in that np.random normal. Okay, so then this is 0 t 0 to 0.1, and in that range it will create 100 data points. Okay, first let me only execute that much, so rest of the things I am putting in the next Jupyter cell. Okay, so let us at least see what kind of data is generated, and you can see that this is my x, there are 100 data points and randomly generated numbers, and similarly these are this is my y, then these are also 100 data points between limits 0 to 0.1, but they are not completely random like this, but at least they are also randomly generated, and each time I execute this, these numbers would change output, but they are at least following some specific distribution, normal distribution, or that means some Gaussian distribution, bell curve like. But it is also not perfectly bell curve because something is added here, 2x. If it would be only this much, then it would be this much, then it would be perfect bell curve between 0 and 0.1, just like this is perfect bell curve between 0 and 1. Similarly, that would be perfect bell curve between 0 and 0.1. Okay, so that are there. Now I want to find correlation coefficient. Now obviously that means this data set X, this whole data set, and this whole data set Y, they are somehow correlated with each other, or we are just finding whether they are strongly correlated with each other or they are weakly correlated with each other. So, and this is very important to find, because in data science, in each and every project of data science, we will have to find this correlation coefficient. Why? That I am keeping at present pending, because for that we will have to do many other chapters later on. But then np.core coefficient and two data sets you have to put. So if I put it, then I get this kind of result, this kind of result. Now I have copy pasted that same result and just made it larger here, okay, and added this. So how to, because that way it is easier to interpret. Correlation coefficient between x and y. So I just added this blue thing. So this is called correlation matrix. Okay, this is 2 by 2 matrix, 2 rows and 2 columns, and this is x, below second row is y, and similarly first column, actually it is 0th column is x, and first column or next column is y. Then this correlation, this one, this particular is 1, and that means how much is x correlated with x? Now obviously everything is correlated perfectly with itself, so in that case between x and x correlation is 1. Similarly, if you see this is, then how much is y correlated with y, because this is here and on this line, so that is correlation between y and y, right? So then that is also perfect 1. Okay, now this is correlation between y and y, but how much is x correlated with y? Then I have to start with first row and second column, because that is the correlation between x and y. So that I get 0.98. And how much is y correlated with x? So that I get this. Now why this correlation is again 0.98, exactly same number. The reason is whatever is correlation between x and y, same is the correlation between y and x. Okay, so that means these two are equal while these two are 1. Now why this correlation is important? That in data science, when you are trying to predict something, say y, using many unknowns, many dependent variables, independent variables, x1, x2, and so on. And this y is my dependent variable, this one. Okay, so in that case, I get, suppose I am making a function of x1, y as a function of, mathematical function of these three independent variables, x1, comma, x2, comma, x3. For example, a very simple function can be y is equal to some constant, say 5, plus some constant multiplied by x1, so say 2x1, plus some other constant multiplied by x2, so say 3x2, plus some still other constant multiplied by x3, so say 1.5 x3. So this thing allows me to calculate value of y provided I know what are the value of x1, x2, and x3. So these x1, x2, x3, they are called independent variables. That is, their value has to be specified, and this y is called dependent variable because the value of y depends upon what values of x1, x2, x3 are specified. Some call these x1, x2, and x3 as features. That is, my y depends on which feature of my data set, then my y, that is the dependent variable, depends upon these three features of my data set. And this y is often called response. An entire data science in all the chapter is nothing but trying to find the response variable, that is unknown y, using the value of feature variable, or in other words, trying to find some such function. Okay, and that function will give me what will be the value of y for any given values of x1, x2, and x3. If I am given x1 is equal to say 2.5, x3 is equal to 1, and x2 is equal to 1, and x3 is equal to 1, and I just plug in those values in this equation RHS, and I will get the LHS. So that whole thing, this equation, that which I am writing in blue, this whole equation is itself called a model to estimate y by using values of x1, x2, and x3. However, what that has to do with this correlation coefficient? The problem with estimation of y is that if there is only one independent variable, x1 only, say x2 and x3 are not there, then the equation would become very simple. Y is equal to 5 plus 2 times x1. That is the simplest case. But in practice, the independent variables, dependent variable y depends upon 10, 12, 15 independent variables. For example, this is suppose the sales of a company, and here this is the spend which the company has done on TV marketing, radio marketing, social media marketing, newspaper marketing x4, then the amount which it has spent on its employee, that is x5, then that is employee salary x, and so on. So there are so many variables that calculating your y becomes very difficult. So at that time, what we do is, suppose there are so many variables, then we, instead of directly putting all of them and finding the model is nothing but one such equation which relates dependent variable and independent variable, or one such mathematical function which relates independent and dependent variable. But as I said, if there are say n dependent variables, independent variables x1, x2 up to xn, okay, and I want to find n can be 20, 25. Now considering all of them, you can understand that this equation would become very, very long. So at that time, what we do is, rather than considering all 20 observations, all 20 these independent variables, we may consider only say 14, and we delete 6 columns. That is, we simply exclude 6 independent variables from our discussion. But the question is, which 6 can be excluded? So at that time, what I do is I find correlation between x1 and x2, correlation between x1 and x2, x2 and x3, x2 and x3 and x4. And if I find that correlation between x1 and x2 is 0.95, so in that case, I will say that whatever information is given by x2, 95% of that is already captured by x1 itself. So then why take both? I can sacrifice around 5% of the information from the data, but I will take only one out of these two. Similarly, if this x3 and x4, suppose the correlation between them is found to be very high, again, say 0.98, like for example here these two data sets x and y were there and I found 0.9844. Then again the question, that means that even if I take any one variable out of these two, then still I am retaining 98% of the information which my data set reflects. So I can delete any one out of these two. So somebody can decide this one and x3 is deleted. But when I find the correlation between say xn minus 1 and n, last two variables. So suppose here there is xn minus 1 and this is xn, and I find that the correlation between them is only 0.25. So that means when I have included xn minus 1, it also captures information, 25% of the information which is provided by nth independent variable. But the question again would be, then what about the other 75% of the information which xn still has? So can I cancel one among these xn minus 1 and only consider only one independent variable out of the two? No, because then 75% of the information which could have been provided by xn, that is lost. So whenever there is high, in short, I can summarize everything in just one sentence, that if two features are having very high correlation, extremely high correlation, then I can afford to cancel or exclude one feature and keep only one of them. But if two features are having less correlation, then I have to consider both of them. I cannot afford to exclude any one of them, because these two are not highly correlated, means they are different features, while these two are very highly correlated, means most of the information of one is already captured in others. So keep any one. That will reduce the number of terms in this long equation, that y is equal to some constant into say 2 multiplied by x1 plus 3 multiplied by x2 plus 1.5 multiplied by x3 plus 2.7 multiplied by x4 plus 5.9 multiplied by, that would become very long equation if I consider all 20 features, that is x1 to x20. But if I could reduce say at least 6 features due to high correlatedness, then this would become a simpler equation or a simple model. And later on we will see that a simple model has many advantages compared to a complex model having all 20 features. So, but how to decide which out of which pair one of the variable can be cancelled or one column can be deleted from my data set without much information? So that is decided by this parameter which is called correlation. So that's why finding correlation is one important skill, and it is simple. You just have to write np.corecof and then print out the result, store the result in some variable. You can even write x, y, anything. There is no need to write this whole long thing, core underscore coefficient. You can write anything here and then print that that parameter gives correlation between two data sets which were given to me. Okay. Now from here, actually, this all thing is just the discussion of what I have explained in my lecture. But from here, some exercise questions will start. Now about this exercise question, I have already written somewhere, not in this exercise. This exercise you will do because we have done enough number of practice questions and enough number of examples on this. But there this chapter will be over and you will get the solution also, okay, in any case. So that this chapter will be over. But in the Jupyter notebook, when I will be providing you, you will see that there will be a lot of content below it, like this, okay. But before that content starts, here I have already written this important note. Let me even put that in some still more prominent way, so that, okay. And I have written that these examples which are given below, they are not for basic or intermediate data science, okay. So they are just kept for the sake of continuity and completeness, so that later on or in some other course or in some other book, if you find some such examples, then you should not feel that why this course did not teach me these things. We are going to cover this, but for that some in-between knowledge is required. So these things are covered in subsequent chapters, okay. Because earlier I thought that I will make 3 courses: basic data science, intermediate data science, and advanced data science. But then I decided that I will make a single course only, but I will keep on specifying at every point that this is advanced topic, so don't touch it at present. So don't touch at present, and if you want to do, you can do, but if you can't understand a few things, for example, what are these agent value and agent vectors, what is this principal component analysis, Fourier transformation, all these things you may not understand. Something you may understand also, say weighted average is not that difficult concept, covariance and correlation matrix is not very difficult concept, so that is fine. But if you don't understand something, then you should not lose heart. So for that I have put that very clear warning here, okay. So students should not be discouraged, and each and everything we will cover in our subsequent chapter. So we will come back to this section after maybe completing around 23 or so chapters, we'll come back to this section, and then you will find, oh, this is so easy. Okay, because by that time all this discussion has been already done. So don't look at this. My advice is don't look at this. Avoid it. Some of you who are exceptionally curious can go through it. Okay, thank you.